I want to invite the next panelists, Nima Arkani-Hamed, Ed Boyden, Andre Linde, Sol Perlmutter, and Richard Taylor. And so as if we did not discuss big enough problems, we're now going to turn to why is the universe comprehensible. So, Nima, what can you say on that?
Damned if I know. Of course, fortunately, the universe is comprehensible. We've been comprehending it for over 2,000 years. I guess what boggles us as theoretical physicists is the fact that the understanding that people have come up with, especially over the last 400 years, starting with Kepler and Galileo and Newton, is that the understanding of the fundamental laws of nature is also fundamentally mathematical. And as time goes on, it involves mathematics that's simpler and deeper and more universal. So, given that fact, you can ask a more specific version of the question: why are the laws mathematical? Why are the fundamental laws mathematical? And over the years, many relatively trivial or tautological things have been said about this subject. But characteristically, Richard Feynman said some in a very pithy way in just a few pages of his wonderful book, The Character of Physical Law, that I recommend you all read. He had something to say about the subject by wondering what it would have looked like if the laws weren't fundamentally mathematical. So you might imagine that really what's going on at microscopic scales is some extremely simple rules, like some gigantic game of checkers or something like that. The actual laws don't involve any deep mathematics, differential equations, fancy things like that, just some sort of simple rules for how things move around, which when you go to somehow very large scales and see only aggregate behavior, end up having a description that looks effectively is governed by more fancy mathematics. He actually described this in the context of the sort of paradigmatic example of what mathematical laws are. The first set of mathematical laws we really understood, which were Newton's laws of gravity. So we all learn in high school that two masses attract each other by the inverse, by force, which varies as the inverse square of the distance between them. And that's a fundamentally mathematical law. But some people after Newton came up with a checkers-like version of an underlying set of rules that weren't so mathematical at all. They imagined that the universe was filled with little particles that were moving around and banging into bodies all over the place. And then if you had two bodies, one here and one there, then if you had a big guy here, it sort of cast a shadow. It prevented the particles from hitting this guy on this side from this direction, and that meant there was more of a force on it from the things banging on it from the other direction. And if you work it all out, it was an inverse square law. Okay, so that seemed to be an example of a non-mathematical underlying set of laws that was approximated by mathematical ones. But that theory ends up being wrong. It makes lots of incorrect predictions. And this has been attempted over and over again in the intervening time. Every time we have a set of laws, people have sometimes tried to find simpler non-mathematical laws underneath it, and it keeps not working. Instead, we find increasingly sophisticated and interesting sets of mathematical laws. And what's even more surprising and gives us gainful employment as a theoretical physicist is that these laws are simple. They have their own internal purpose. On the one hand, coming from trying to describe nature, but quite amazingly, our friends, the mathematicians, from their own explorations, not of the universe, but of the Platonic world of ideas, run into very similar structures. And that's absolutely amazing and completely ununderstood, I think.
Well, it's already simple enough so that I understand there are roughly 10 parameters that define everything. And the question is, why not 1,000 or 10,000?
Yeah, that's a good example of a question that we don't know the answer to. I mean, but notice that the number is like 23 or something like that. It could have been 2, it could have been 20,000. It's a funny intermediate number. The fact that it's a funny intermediate number probably means that this particular question is not as close to the really deep fundamental questions as we might like them to be. They might be still a few layers removed from when the questions are well posed enough to have simple answers. Part of the chauvinism of at least a certain part of fundamental physics is the belief that the only questions we really care about are the ones that have fundamentally simple answers. and if the answers are very complicated, well, that's probably not a clue to what the deeper underlying theory is. That may be a prejudice, it may be wrong, but it's been a good guide for the past 4 centuries.
So, Richard, why mathematics is the language in a way that you discover similar structures that then are being useful for physicists?
I wish I knew. To some degree, I think, or to a large degree, mathematicians are inspired by what the physicists are doing. Although in theory one can sit by oneself and use pure logic and invent mathematics and potentially do very interesting mathematics, that's not usually what happens if our imaginations are not sufficiently good to find the really interesting mathematics. And very often it's inspired by something far more concrete, maybe doing numerical experiments with the integers, counting. Gauss did lots of experiments, found patterns of how the prime numbers were distributed. More recently, Birch and Swinnerton Dyer revolutionized number theory by computer experiments that showed patterns nobody had imagined. And then equally, physics is telling us things. Mathematicians had been interested in curves lying on more higher dimensional things, and physicists suggested there are certain patterns here that mathematicians had never imagined existing, and now many, many mathematicians are investigating this. So somehow the physical world provides inspiration that just pure logic doesn't seem to do.
Andre, you're one of the authors of multiverse concept, and what do you have to say on the subject? But more specifically, do you think there could be a universe that cannot be explained by simple mathematical laws?
Well, what I can say about that.
You have a microphone?
What? Oh, yeah, okay. So, during the last 30 years, we have a new theory which tries to explain why the universe is so uniform, because this was the main basis of Einstein's approach to it. Everything is uniform, and probably the coupling constants and everything should be just given in the way they are. We don't have any choice. But then we learned that if we follow the logic of the new cosmological theories, then most probably our universe looks very, very similar in our immediate vicinity, but very, very different far away from us. So when Einstein asked a question, he formulated this question, that why is the universe so comprehensible? He said that the most incomprehensible thing about our universe is that it's comprehensible. So when he formulated it, and then Eugen Wigner, actually a mathematician, said a very similar thing from the point of view of mathematics, that incredible efficiency of mathematics with respect to natural sciences like physics is a gift which we do not understand and don't deserve. So physicists say we do not understand physics. Mathematicians say that we don't understand mathematics, or why anything works. And on the other hand, if you have a universe which actually is a multiverse, which is what many of us think about right now, then there are some parts of the multiverse where quantum fluctuations are so strong that you cannot remember anything, you cannot calculate anything, whatever laws given to you, you do not recall. And there are some other parts of the multiverse where you cannot live because it's totally empty there, or the universe is rapidly collapsing. And there are some other parts of the multiverse where laws are too primitive to allow complicated forms of life like we exist. And there are some other parts of the universe where we can live, but we cannot remember anything. And if we do not remember anything because whatever, quantum fluctuations erase our memory, again, mathematics and the way of predicting future would be impossible. So in that part of the universe, well, computers will be unable to survive in the competition of whatever, some primitive organisms. So it's not that laws of physics and mathematics everywhere are efficient, but we live only in the parts of the universe where laws of mathematics and physics locally are efficient enough to allow us to win the game of evolution.
Ed, how does the human brain comprehend the universe from coming from a different angle?
Yeah, so I can start by building off from what you were just pointing out, and in order for, let's turn the question on its head a little bit. When asking how the universe is comprehensible, we should talk about what comprehension means, right? And it's quite possible that a mouse or a rat that's wandering around feels perfectly at home, and it feels like it's comprehending, maybe. It's a little speculative there. But it's not asking the tough questions. And going back to what you were saying, earlier, it's quite possible that we're not asking the tough questions either. We admit defeat on many questions, and we go back and study things that we can really nail down as a civilization. And some of that's practical, right? We want to tackle problems where you can make, good progress in an appreciable amount of time, and there's really not a lot of reward for banging your head against a wall incessantly for many decades, and so there's a lot of stuff that are really difficult to challenge. So in the first panel, the topic of what exactly is consciousness came up, and I don't think they quite answered it. That's one that I think is no. I think that's one that if you ask 3 neuroscientists, you probably will get 4 different answers. And we survive, of course, by breaking things down into parts that we can analyze. So, things that our mind is good at, we extract rules, right? We find patterns. That's comprehension to some extent. And some of those patterns can lead to laws of physics. Trying lots of experiments and looking for what commonalities emerge. There's also prediction, right? If you need to predict the future for a little bit. If you are trying to escape a predator or hunt prey or reproduce or find food or whatever, you have to be able to forecast a little bit into the future in order to actually make any headway. And so, these are things that under evolutionary pressure, and of course many different kinds of pressure that are all coming from all different angles, of course, our minds have evolved to confront. And so there's definitely an element there of sort of an anthropic principle. If a piece of the universe where we really couldn't predict the future for a little bit and detect patterns, we wouldn't survive very long. And intelligence takes some time to achieve, at least 100,000 years, I guess, from the previous panel. So we have to be able to kind of play the game for a while in order to get to the point where comprehension is possible. I mean, the very interesting question is, as we start to understand more about the mind, and of course there's a lot of interest in artificial intelligence right now as well, could you engineer algorithms or systems that could understand more of the universe? What if we are the mouse or the rat on the ground, answering the problems that we are comfortable with, but shying away from the really tough issues? What if we can build some algorithms or systems that can understand more? And what would that be like? What would it be like to cooperate with them? Could we actually augment our own understanding, or would we have another system which could crunch the numbers, but we would never feel the visceral feeling of, yes, I got it. I actually intuitively grasped that. And I think there's a lot of that too that's important in physics.
I think that's already happening in mathematics. Things like the Kepler conjecture, which was in some sense solved by Tom Hales. It says that if you've got a lot of balls all the same size, how can you pack them most densely in space? And the supermarkets know the answer. If you look at the oranges, they're arranged in a certain pattern. But Kepler asked, is this really the densest way of packing balls in usual space? And no human comprehends the answer, but a massive computation really of lots of many possibilities by a computer has shown that indeed it is. That's something that seems to me quite possible. No human will really ever understand. It may just be beyond our abilities of our brain to compute, but it's a beautiful fact, and the only explanation is too complicated for us. There are other examples that the four-color theorem that says if you have any map, you can color all the countries in just four colors so that no two countries that share a boundary are the same color. Maybe that has a nice explanation, but at the moment the only reason we know it is that computers have plowed through millions and millions of possibilities and no human understands it. And could it be that physics is the same, that the fundamental yours you're searching for are actually beyond us?
Nima, could it be the same?
I doubt it. Well, I mean, I think first that there are a few things that were said. There's one.